This series of screencasts is designed to give an overview of undergraduate reactor design. It's assumed that you've seen it before, so this is just a review. So I'll go through some subjects relatively quickly. Please contact me if you have any questions. This first screencast reviews mole balances, and it's based on the way that the material is presented in Scott Vogler's book, but it's also the same kind of material as in Hill and Root's book on chemical kinetics and reactor design. So the starting point is just to think about reaction rate. The rate, as we've already discussed in our course, is defined as the moles of a species produced per unit of volume per unit of time. And while it should be clear from some of our discussion from batch reactors, the way that this is sometimes written as the rate of a reaction being the rate of change of the concentration of a species with time. But this may not be the right way to write the rate of a reaction all the time. And one of the most obvious ways to see whether this is correct is to think about what happens in a CSTR. So we're going to start talking about different types of reactors. You probably recall that a CSTR is a continuous stirred tank reactor, or a mixed flow reactor is another term that's used. And the idea is that it's completely well mixed, so there's a tank, it has an impeller or some other way of stirring, and it's well mixed at all times. We feed in reactants and we remove products and any unreacted reactants as well. And generally these reactors can be thought of as operating at steady state. But if they operate at steady state, the rate of change of concentration in this reactor is 0. But we expect that if this reactor is doing something, the rate of reaction is not 0. So that suggests that if our reactor is doing something, this equation must not be correct. So we need to take a different approach. Now, as you are aware, this equation can be written for a batch reactor at constant volume. But for general flow reactors, we need to have a more general approach that's going to work for any system. So we need a mole balance, and we need to consider flow as well as generation of material. So the way we do a general mole balance is we define a unit of volume, which is sort of here. It's written as this general shape because it doesn't matter what the shape is, but the assumption is that inside of that little volume, the concentration of all species is homogeneous. Now the terms that we need to consider are molar flow of material into this volume, and we'll call that F sub j, it's species j we're talking about, and subscript 0 or not to represent that it's what's going in. What's coming out is F sub j, and the rate of generation inside of this volume is G sub j. So we expect that a general balance should look like the flow in, the generation of material, equals the flow out plus any accumulation that occurs. So we can write that as Fj naught plus Fj is equal to Fj plus the rate of change of the number of moles inside of this volume. By definition of rate, the rate of generation should be given by the rate of production of A times the volume. And the rate of reaction should depend on temperature and concentration. We're very familiar with this by now because we've talked about kinetics in great detail. And in more general terms, we can assume that our reactor is made up of several homogeneous volumes, which I might call delta V sub I. So I here is just an index that represents any number of control volumes. And so delta G for species J in volume I, sorry, I accidentally tapped this for too long, so I need to restart it. So the rate of generation in subvolume I is given by the rate of reaction in that subvolume times its volume. And the same thing can be done for subvolume 2 and any number of subvolumes. And so the overall rate of generation would be the sum over all subvolumes, all of which are homogeneous, of the rate of reaction in each one times the volume of each one. In the limit as the subvolume goes to 0 and the number of these subvolumes approaches infinity, this looks like an integral. So the rate of generation in general, is given by the integral over the reactor volume of the rate of reaction. With that in mind, the mole balance then for a continuous reactor looks like the rate of change of the number of moles overall is the flow rate in minus the flow rate out plus the integral of the rate of reaction throughout the reactor. So for a batch reactor, what this looks like is what we've seen before, basically. The rate of change of the number of moles, because there's no flow, is given by this integral over the volume of the rate of reaction. And we need an initial condition, so at time 0 we add those reactants, and we know their concentrations initially. Now if the reactor is homogeneous, this rate of reaction is constant with respect to position at any given time. So this integral just becomes the product of the rate of reaction times the volume. So we get an expression that looks like this, and if we rearrange that, we get the rate of generation of species J is given by 1 over the volume times the rate of change of the number of moles, which is an expression that we've seen before. If the volume is constant, we can write that the rate of reaction is given by the rate of change of concentration, because we can take the volume inside of that derivative. If not, in the general case, the rate of generation of a species is given by 1 over the volume times the rate of change of the product of the volume and the concentration, which is the rate of change of concentration plus the concentration over volume times the rate of change of volume. So we may need to use this expression for a non-constant volume reactor. For a CSTR, that's a continuous reactor which is well mixed, and it's well mixed. So what that means is that the integral becomes just the product of the rate of reaction times the volume, because the rate is constant everywhere. We have a flow in and a flow out and a rate of change of the number of moles in the reactor. If the reactor operates at steady state, which is the usual case considered in undergraduate reactor designs, this rate of change of the number of moles equals 0. So the design equation looks like this. It's an algebraic equation, and the volume of the reactor can be calculated from the flow rates in and out divided by the rate of consumption of a species. For a plug flow reactor, the simple assumption is that we have a well-mixed system radially, but as we move axially along the reactor, we're going to see a change in the concentrations of species. So this integral of the rate of reaction with respect to delta V, if we just look at this small slice, is the rate of reaction times delta V. And we assume that the system's homogeneous within that very thin slice. So at steady state, the design equation, or the mole balance, ends up looking like the flow rate in, which is the flow rate of species J at position Y, which is here, minus the flow rate out, which is the flow rate at position Y plus delta Y, which is here, plus the rate of reaction times the cross-sectional area times delta Y, the thickness of this slice, equals 0. Curses. Okay, I'm back. And if we rearrange this and take the limit as delta Y goes to 0, this becomes a differential equation. So the rate of change of the flow rate of species J with respect to position is given by the cross-sectional area times the rate of reaction. Even if the cross-sectional area is not constant, we can work in terms of the volume of the reactor. And a similar balance leads to this expression: the rate of change of flow rate with respect to volume is equal to the rate of reaction. Taking Fj being equal to Fj naught at the inlet and rearranging this equation leads to this differential expression. And if we integrate from 0 to the volume at some point in the reactor, that's equal to the integral from the initial flow rate to the final flow rate of 1 over the rate of reaction. So this is the design equation for a plug flow reactor. The volume is equal to the integral from the final flow rate to the initial flow rate of the differential of the flow rate over the rate of consumption of a species. And one last type of reactor we can consider is a packed bed reactor, where it looks like a plug flow reactor, but it's packed with catalyst. We can make similar derivations to what we do for a plug flow reactor, except that we replace the rate of reaction per unit of volume with the rate of reaction per unit of mass of catalyst, rather than the volume. And it turns out that the expression is very similar to what we have for a plug flow reactor, but the weight of catalyst is given by the integral from the final flow rate to the initial flow rate of 1 over the rate of consumption per unit of mass of catalyst instead of per unit of volume of reactor. So that's the simple, quick introduction, and it summarizes Chapter 1 of Fogler. And the summary is, for batch reactors, of course, we have long residence times, modular designs, but the disadvantages are that there's downtime required for cleaning, and there may be batch-to-batch variations, but it's good for small batch kinds of processes. A continuous stirred tank reactor is, of course, continuous, and it gives a consistent product and makes temperature control relatively straightforward. but large volumes are required to make this worth doing. A plug flow reactor is cheap and easy to build, and it can be built into heat exchangers, and you can also pack a catalyst into the tube. So that's the advantages. The disadvantages is that you can have temperature run away at certain points and there can be hot spots. We'll talk more about that when we talk about energy balances. So that's the end of the introduction to mole balances. I'll say more in the next screencasts about design of reactors.